Yes, okay. Good, okay, so I guess the different topics today will seem somewhat disjointed because it's really a loosely connected series of topos all about the gamma function. Gamma, gamma, gamma. So first I'm going to beat a dead horse. I almost said beat off a dead horse again. I'm going to beat a dead horse slightly and do a quick warm-up exercise with supremum and infimum, so we remember the definitions. Then I just want to talk about a lot of gamma stuff. So the history of the gamma function from the alternate perspective of trying to get a continuous version of the factorial. Then we'll talk about how to generalize the derivative to non-integer order. You can take a first derivative or a second derivative, and now we'll take a 1/2 derivative, for instance. We'll talk a little bit about the beta function, which is related to the gamma function, and appeared in the first equation of string theory. And then we'll talk about this Euler or Euler-Mascheroni constant lowercase gamma, which you've now seen in two contexts. It appeared in the solution to the coupon collector problem and also in this formula you wrote down today for maximizing the volume over dimension for an n-ball with a fixed radius. So good, that is the plan. First let's do the horse and do some supremum infimum stuff quickly. So again, why is this important? We saw this definition, this very central definition of volume or measure in any number of dimensions, and the way that it worked was if you wanted to find the measure of some non-elementary set E, so E could be like this circle or something, you really consider all, I guess I should call this A or something, all A's that are elementary and contain E. So the point of this thing is that E itself is not elementary, but if you consider all the bigger sets A that are elementary and contain E, so for instance, this set, set of all measure of A's, for instance, this is going to include some huge numbers, right? Because you can make an arbitrarily giant box that contains E. So this set itself isn't very useful because this contains huge, huge, huge measures that have nothing to do with E, right? But if we take the infimum, which is the greatest lower bound of all of these things, remember the infimum is not in the set in this case because E itself is not elementary. So the measure of E is not in this set. But the greatest lower bound of this thing, if the set E is measurable, Jordan measurable, will be the measure of E, the greatest lower bound of all of these sets. Similarly, if again this thing is measurable, you can consider all elementary sets, say, B, that are contained in E, and then look at the set of all measures of B's. And again, this set altogether is not that useful because this contains arbitrarily small boxes that have measures very close to 0. So the set contains, measures that are extraordinarily small and then measures that get closer and closer to what we want to define as the measure of E. So what we really want to do is take the supremum. And this is why it's absolutely crucial to realize that the supremum is not the largest element of the set because the measure of E is not in the set. The supremum is the least upper bound. It is a number which is greater than all of the elements in this set, and is the smallest number with that property, that it's greater than all of the elements in the set. So if these two things are equal, we say this thing is Jordan measurable. So that was the point. Supremum and infimum appear in a key way. Okay, good. Thoughts or questions on this quick review?
Yeah, I was getting ready to rattle off the definitions of supremum and infimum, but
you were ready.
Yes, the point is clear.
You were ready for the horse. Prepare your anus because the horse is coming. It's like that Mr. Hands video. Okay. Have you seen the Mr. Hands video?
No. Why would you want to?
Good question. Okay, so let's do a quick challenge then. So I'll define the set A, which is the set of all inverse integers, or harmonic, 1 over n's, if you will. So this has 1 over 1, 1 over 2, 1 over 3, 1 over 4, blah, 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 all of those for integers. So I'll ask you 3 questions. First, you can state the answer without proof. So what is the infimum of the set A?
0.
Good, it is 0. Okay, so next we're going to prove that. To remember the definition, if we want to prove the infimum of A is 0, what 2 things do we have to show?
Okay. So we need to show that some value C is less than all values in A.
What is C specifically, though?
the infimum that we want to find.
Which you're claiming is 0.
Or,
Right?
pardon me, we want to find that C is a lower bound, and then that it is the least lower bound.
Greatest lower bound. And
I mean, yeah.
yeah, so, and not just C. If we're trying to prove the answer is 0, then we want to prove 0 has that property, right? So,
yeah,
so 0 is less than or equal to, I don't know, lowercase a for all a and a. And then you say 0 is the greatest number with this property. So greatest, my handwriting has gotten quite bad. Greatest number satisfying 1. Okay, so I'll ask you now to just prove it. The first one is very easy. So how do we prove property 1, which is that 0 is less than or equal to every number in the set A?
I am tempted to think that this is along the lines of noting that there's a 1 in the denominator of A. Well, of all elements A.
What do you mean a 1 in the denominator? Like 1 over 3 is in here. So what do you mean by 1 being in the denominator of 1/3?
I mean, numerator.
Yeah, okay, good. So you're saying the numerator is positive and the denominators are all positive integers, right?
Yes.
So another way to say that is, if n is positive, then, that means we can say, 1 over n is also a positive number for any positive integer. So thus, all a and a satisfy that a are greater than 0. So that's enough. I mean, all we have to do is prove that they're all greater than or equal to 0, but it certainly works if they're greater than 0. Okay, good. So that's just a statement that if you take a positive number and then take the inverse of that number, it's still positive. Good.
Okay.
Now the trickier part, how do you prove that if there were any other number that were a lower bound of a, that number must be, if there's any other lower bound of a, then that number can be at most 0. That 0 is the greatest number with this property.
I believe we suppose, by way of contradiction, that there is a lower bound greater than 0.
Okay, so good, that's a good start. So suppose y greater than 0 is a lower bound, and then we have to get a contradiction, right? So how can we get a contradiction?
I believe that we can simply make n large enough that such that 1 over n is less than y.
Yeah, so choose n large enough. So in particular, you can just take, say, n greater than 1 over y, right? Because if n is greater than 1 over y, thus you just take invert both sides. That means 1 over n is less than y, because you have to flip the sign of the inequality, right? So choose n large enough, then 1 over n less than y, which contradicts that y is a lower bound. Good. Very nice. Okay, good. This one's a pretty simple exercise, but it's important to remember these two properties that are kind of the key definition. So indeed, as you said, the infimum is 0. We have to prove it's a lower bound, which is easy because every element is 1 over a positive integer, and 1 over a positive integer is still positive, which means it's greater than 0. So the first statement is easy to prove. And then almost exactly as you said, if we had some other lower bound, say epsilon, greater than 0, you could always just choose an integer larger than 1 over epsilon, which would get a contradiction. So yes, the horse that we are beating is that the word infimum means the largest of all lower bounds. That's the only definition. Okay, so one more exercise. So we're going to suppose a and b are non-empty. So I'm just going to draw a number line to help us visualize. So a and b are non-empty, and we're going to assume that every x in a is less than or equal to every y in b. So visually, if a doesn't have to be an interval, but it could have an interval here, an interval here, maybe a point here. So blue equals a. But then we're assuming that everything in b is supposed to be larger, or larger than or equal to. So you can have, say b here, where it's equal to an element of a, but then b all the way over here, green has to be b, green equals b, all of the elements in B have to be greater than or equal to all of the other elements in A. So we couldn't have an element of B over here, because then it would be less than some elements of A. Okay, so that's what it looks like. Good. If that's true, can we prove that the supremum of A is less than or equal to y whenever y is an element of B? So how could we prove that?
I feel like this is another proof by contradiction.
I think we could do this one directly, just from the definition of supremum.
Okay. Let's see. Okay, we are told that quote-unquote all of A is less than all of B. I'm just compressing words.
Yeah. So in particular, if y is any element of B, then y is an upper bound for A, right? Because y is greater than or equal to all elements in A, right? Another way to say
yes. So the supremum of A is the value such that it is greater than or equal to all elements A and is the least of all elements such that that supremum is greater than A.
Okay, so you said, yeah, the supremum of A is greater than or equal to all elements of A, but in other words, it's an upper bound, and it's the smallest such number, right? Good. So then, if y is any element of B, how can we conclude that that means y must be greater than or equal to the supremum?
I guess if the Sorry, could you say your question again?
I was just saying, how do we prove
statement.
Right, so how do we prove A?
So
well, we want to prove this is true for all y and b, so we should probably say, okay, so let y and b. And we want to prove that that means y is greater than or equal to the supremum. So what do we know about y by assumption? If y is any element of b, what do we know from the problem?
We know that y is greater than or equal to x.
Y is greater than or equal to x for every x, right?
Yes.
For every x in A. Okay, so what does that mean?
This means that it is either true that the supremum of A is equal to the lowest, well, the supremum of A
okay, pronounce it
is
supremum.
equal to supremum.
Supremum, but go on.
Supremum of it, I think. I think.
So the statement that y is greater than or equal to x for every x in A, what does this mean? So, in other words...
That means that y is an upper bound of y. I mean, of B, sorry.
Of A. For every x in
of A, sorry.
So y is an upper bound of A. Okay. So if y is an upper bound of A, and the supremum is the least upper bound of A, what inequality does that imply about y and the supremum?
That implies that y is greater than or equal to the supremum of A.
Yeah, so we're done. That's it. The only thing we needed to do to prove A is say, suppose y is any element of B. We've assumed that that means y is greater than or equal to x for every x in A. We just remember that's the definition of upper bound, so y is an upper bound of A. But then the definition of supremum is that the supremum is less than or equal to every upper bound of A. So if y is an upper bound, then by definition, the supremum is less than or equal to y, since y is an upper bound. Right. So that proves A. All you have to do is remember what the definition of each word means, and then chain them together, right? So we assumed this. You just have to remember that this means the words y is an upper bound of A, and then you just have to remember what the word supremum means. The word supremum means it's less than or equal to every upper bound of A. So good. It's just remembering the words. This is why it's crucially important to be able to say the definitions of things verbatim, right? The supremum is the least upper bound. That means it's less than or equal to every other upper bound. Because, I mean, that's what you do when you write a proof, is just concatenating sentences where each one follows from the previous one. Okay, so a little trickier. How can we prove now that the supremum of A is less than or equal to the infimum of B?
So we are told that the supremum of A is less than, well, we've proven that supremum of A is less than or equal to y for all y and B.
Good, yeah, that was part A. Okay. For all y and B, I agree. How does that help us?
The infimum of B is the value such that it is infimum B is less than or equal to y for all y and B. Wait. Yeah.
That's one of the properties. Yeah, infimum is less than or equal to y for all y and b, and it's the greatest number with that property, right? As you told me a moment ago.
Yeah. It seems like it would be easier by contradiction.
Okay, yeah, I think that's probably smart. So, okay, so suppose the opposite. So what is the opposite of this statement? How do we negate this?
So suppose the supremum of A is greater than or equal to the infimum of B.
Not greater than or equal to, just greater.
Ah, yes, greater than.
Yeah, it's not less than or equal to, then it's greater. There's only three possibilities. Okay, so...
Wait, infimum of B.
Oh, so good, yeah, thank you. Good, infimum of B. Okay, so I think it's useful in doing this proof to give these guys specific names. So maybe let's make the supremum of A alpha and the infimum of B beta. And something I found useful in writing the solution for this was, then why don't we just take the difference between the two of them? Because if you say alpha is greater than beta, then that means supremum of A minus the infimum of B. In other words, alpha minus beta is supposed to be positive, right? So alpha minus beta, why don't we give this a new name, epsilon, and say that's positive. So the thing we're assuming to get a contradiction is that the difference between the supremum of A and the infimum of B is some positive number epsilon, right? So in other words, if here is A, and then alpha is here, and then alpha is supposed to have some finite distance epsilon. So here's beta here. So what we're assuming by way of contradiction is that this little distance here, alpha minus beta, is some positive number epsilon. Okay, so that's just the picture of what you told me for the contradiction. But the picture suggests what we should do next to get a contradiction, right? Because we assumed that every number in B is supposed to be greater than every other number in A. But now you see this overlap here. There's some overlap here where some numbers in B are less than some other numbers in A. So that's how we're going to get a contradiction. But do you see how to write that more precisely?
All right. So we then see that, let me think. There must be values where alpha is greater than beta.
There must be values. So
I mean, not value. It must be true that alpha is greater than beta.
yeah, good. So, well, that's what we assumed up here, right? Alpha greater than beta
Okay.
is what we assumed
Yeah.
for contradiction. Good. Yeah, so the thing we're trying to contradict.
So,
oh, sorry, go on.
I think. I know that I need to somehow word that there exist values of A greater than values of B.
Yeah, good. So we should actually pick them. So we're trying to construct some A in A and some other B in B.
Okay.
And
so
how do we build those? How do we get some A bigger than some B using this?
Let us define a value A such that A equals alpha minus 1/4 epsilon.
Okay, A equals alpha minus 1/4 epsilon. Okay. So now we have to prove why must there be some element A belonging to the set A such that A is greater than alpha minus 1/4 epsilon. How do we know? How do we know that there actually is an element in A which is bigger than this one I've written in brown up here? You have to prove that there exists such an element, right?
Well, for I'm not entirely sure we can prove that point exists.
We can't prove that this exact point exists, but can you prove that there must be at least one element between this value, alpha minus 1/4 epsilon, and alpha? There has to be at least one in here. How do we know that there must be at least one element in A between this guy and alpha?
Oh, because okay.
What would happen if there was nothing in A between this guy and alpha?
If there was nothing in between that value and well, if there's nothing in between that value and alpha, then then the supremum of A would not be the least upper bound.
Good, exactly. Yeah, if there were nothing between alpha minus 1/4 epsilon and alpha in A, then this guy would be an upper bound as well, right? That's the definition. If there's nothing in A bigger than this guy, then this guy, alpha minus 1/4 epsilon, is an upper bound, which contradicts that alpha was the smallest upper bound. Perfect. Okay, so you say there must be, I guess I should give it another name, there must be some A tilde in A with A tilde bigger than alpha minus 1/4 epsilon, or else this A, this number here, alpha minus 1/4 epsilon, would be a smaller upper bound. Perfect. Okay, how does the same argument work to get some guy in B?
Okay. We let B equal beta plus 1/4 epsilon. I'm getting Discord messages, I'm scared. Yeah, I'll worry about it later.
Good. Okay, so why must there be something in B bigger than this?
So, once again, there must be a B tilde in B such that B tilde is less than or equal, less than beta plus 1/4 epsilon.
Yeah, good. Yeah, there must be something smaller.
Or then it would be a greater upper bound than the greatest upper bound.
Greatest lower bound, right? Infimum is the greatest lower bound. Supreme is the least upper bound, right?
Yeah.
Beta would not be the infimum. Okay, good. So then last step. So what's the contradiction? Now you know that there's a B tilde and an A tilde with the properties that A tilde is bigger than B tilde. So then what happens?
But we were told that for all x in A and all y in B, that x is less than or equal to y. But we have found two values where A, well, A is greater than B? Well,
Yeah.
A tilde is greater than B.
Yeah, you found this guy greater than B tilde, contradicting that it's supposed to be the other way around, contradicting x is less than or equal to y for all x in A and y in B. Perfect. Okay, so let's just recall what we did. The contradiction, the proof by contradiction first, this is what Terry Tao calls giving yourself an epsilon of room. So we wanted to prove that supremum of A was less than or equal to infimum of B. We gave ourselves an epsilon of room by saying, suppose by contradiction that there was some space between the two, that the supremum of A was actually bigger, and then using that epsilon of room, we split these guys by saying there must be some alpha tilde over here by the definition of supremum, and there must be some B tilde over here by the definition of infimum, and then that splitting gave us a contradiction because we could force A tilde to be bigger than B tilde. Good. Very nice proof. Okay, good. I'm glad we worked through that. Questions on this argument, or are the steps in logic clear?
Everything is clear and I have no questions. Do you mind if I try to track down a soda?
Sure. I'll be here.
Mission accomplished.
Ah, you are no longer out of Coke Zero. Is that right?
That is correct.
Excellent. Good. Okay, so the solutions match almost verbatim what you said. In the first case, we just had to show that y is bigger than the supremum for all y's, but by definition, or by assumption actually, y was an upper bound, and supremum of A is the least upper bound. So therefore, the least upper bound must be less than or equal to every other upper bound, and y is such an upper bound. And in the second case, we split them with this alpha beta thing, assume that there was some space epsilon between them, and then, so you used epsilon over 4, and I used epsilon over 2, I think. So you were a bit more conservative, but
I used epsilon over 2 because, I used epsilon over 4 because then those two would be equal.
But I said less than, not less than equal. So, right.
Clap.
They're strictly less than and greater, then I was still safe, but I was pushing it to 1 point. So, good. Okay, well, I think that reasoning is clear. This was just point splitting with epsilon to give us some room. So let's talk about gamma. Just go through this collection.
Is gamma a function like sine or polynomials or log or so on?
Yes, but in what sense? How, like those, how?
What is the...
Analytic.
What's it? Transcendental. Is gamma transcendental?
Yes, yeah. Gamma is certainly transcendental. Okay. It's also analytic, and it's smooth. Except
Wow, that's magical.
Yeah. Well, we'll learn about analytic function theory in the next chapter, but yeah, gamma is actually the unique way of continuing the factorials that is analytic. So this is why it's especially nice. But it's certainly transcendental because it's defined by some integral. But um, okay, so to remind us, last time we met the gamma function in the context of finding the volumes of spheres, and I signaled that there was, a completely parallel development that sort of led to people studying the gamma function. So let me just tell you briefly about that. This actually started in the 1720s when Daniel Bernoulli and Goldbach kind of simultaneously started looking for a way to connect the points on the factorial. 0 factorial being 1, which actually doesn't work for gamma, but that's why it's shifted by 1. So 1 factorial being 1, 2 factorial being 2, and so on. And they wondered, can you connect those integers, this kind of discrete point set, into a continuous curve? And I think it was actually, they were talking to Euler, and it was Euler, who I've drawn here, put in a picture of here. Euler solved the problem for them first in 1920, and then he had a small update in 1930. So he actually wrote down the solution to this problem, which is the gamma function.
What is he wearing?
It looks like he's wearing pants on his head. I have no idea what that is, to be honest.
You can continue, because I had to point it out.
Yeah, it's a little weird, but he's apparently a strange guy. Leonhard Euler liked to wear pants on his head. So anyway, so the first form in which Euler wrote down the solution to this problem, the generalized factorial, which later became the gamma function, he wrote it down like this, which looks very different from the way that we wrote it last time, which had like this t to the z minus 1, e to the minus t or something. So first, just as a historical exercise, I'll challenge you to show that this first way that Euler wrote the gamma function is actually equivalent after a u substitution to the way that we wrote it last week. So that'll be this challenge. So just to remind us, here's what Euler wrote down, this generalized factorial for n factorial. And then what we wrote last time was this gamma of, I shouldn't put x there because I've written z on the right side, so there should be gamma of z, I guess. So we defined gamma as a function of z as this integral over t, which runs from 0 to infinity and looks very different. So I'll ask you, what happens if you take the definition that we had last time involving t and then make the change of variables t equals minus logarithm of s and then do a u substitution? So walk me through what happens if I do that.
Alright, we make the substitution t equals negative log s, where dt equals negative 1 over s times, ds.
Good. Okay, and then what does this integral look like?
Let's see. It's going to be... I'm trying to think about... Oh, that's lovely! Okay. So, ds equals negative s dt, which is in turn equal to... let me think about how to word this right.
Yeah, you can also solve this t equals minus log s. You could write this as log s is minus t, or s equals e to the minus t.
Yeah, that's what I was looking for. Okay. I was trying to remember, so, like, the log and e to the power of stuff. Anyways, so s equals e to the power of t, and that's going to be useful.
Minus t, but yeah.
It's going to be, yes, e to the power of minus t. So, negative log s to the power of n becomes why is this t to the n?
Yeah, so this will be, well, we'll have to change the endpoints as well, but this will be t to the n. What do I put in for the ds?
And ds is going to become negative e to the power of negative t?
Negative e to the negative t dt. Now the tricky part, how do the endpoints change?
Let's see. T equals negative log s.
Well, the top one's easier. When s is 1, what happens to t?
So, let me see. When s is 1, we get it going to negative 0.
Yeah, so 0 at the top. The bottom is going to be an improper integral, an improper bound. So in the limit as s goes to 0, what happens to t equals minus log of s?
It goes to infinity.
Yeah, so we have an infinity in the bottom bound. So now do you see how we can
And we can multiply, well, not even multiply, we can change the order of the bounds of integration to get e to the power of negative t times tn.
E to the minus t, t to the n, dt. Good, and we swap the bounds to get rid of this minus sign, which gives us 0 up to infinity. Okay.
Oh.
Now, what is this in terms of the gamma function that we wrote before? Because this is not gamma of, oh wait, why did I write? Yeah, okay. This is not gamma of n. What is this evaluated at in terms of this gamma that we wrote down here?
Let's see. Are we seeing n equals z minus 1?
Yeah, good, because the integral that we just got has t raised to the power n, but in the definition of the argument of gamma, this is z minus 1. So the two things match only if z minus 1 equals n, or z equals n plus 1, right? N plus 1. Do you see why? Because if you take this n plus 1 and plug it in, whereas we see z in the formula down here, then we're left with t to the n, which matches the first line, right? Okay.
Okay.
So the two match except for this weird shift of 1. So just to remind us of what this is equal to, we were trying to generalize the factorial to non-integer arguments, but the gamma function is not exactly equal to the factorial, it's shifted by 1. In other words, n factorial is gamma of n plus 1. So this is, I mean, it's not a huge deal. It's a weird, just one-off shift, but it will be important. So again, just to see that one more time, as you see, if we take the Euler formula, this n factorial 0 to 1 minus log s, whatever, raised to the power n, do this change of variables, the guy inside becomes a t to the n, put in the ds being minus e to the minus t dt, and then the bounds become infinity and 0, as you said, spend the minus sign to trade them, and then we're left with 0 to infinity integral t to the n e to the minus t, which is gamma of n plus 1. Okay, so this, again, is the off by 1 thing of the gamma function. Did you spill soda halfway through that sentence?
Yes. You finally asked about it.
I was waiting to see if you were going to tell me to stop talking so you could clean up the soda. Is it okay, or do you have to?
I have napkins right next to me. It's not a big deal.
Good, good. It's funny. Okay, good. So, well, anyway, now we've matched our notation to Euler's notation when he first wrote it down. Okay, so one more challenge. If this thing is actually the factorial, we should try to compute it for all the integers. So in this challenge, we'll write down the value of the gamma function at every integer argument. But it'll be very easy, because we can do it by induction. We only need to compute gamma of 1, because we already proved last week that gamma of n plus 1 is n times gamma of n. So if we know it at 1, then we know it at 2, because gamma of 1 plus 1 is 1 times gamma of 1, and so on. So I'll just ask you, if we try to, again, I put x instead of z, if we plug in z equals 1 to try to compute the gamma function at 1, what integral do we get, and what is its value?
All right. So gamma of 1 equals the integral from 0 to infinity of t to the power of 0 e to the negative t dt.
Good. T to the power 0 is also known as 1. Good. And then what's this?
The integral of e to the negative t equals negative e to the negative t.
Good. At infinity and 0, and then what's that?
At infinity, that is 0, and at 0, that is, well, negative 1. So 0 minus negative 1 equals 1.
Good. Okay. So that means gamma of 1 equals 1. And then using this formula that we proved last time by integrating by parts, gamma of 1 plus 1 is gamma of 1, which is 1. And then gamma of 2 plus 1 is apparently 2 gamma of 1, which is 2, and then it continues onwards. So 1, 1, 2, and then 3 times 2 is 6, and then so forth. So this actually proves that it has the factorial property, right? Because the first integral gamma of course, why did I put a 0 there? I meant 1. Plugging in x equals 1 gives us an integral of 1, and then you can go on to get the factorials for all of the rest of them. Good, so this actually proves the property that we wanted, that gamma agrees with the factorial up to this shift of 1 inside.
Random thought. We are 15 slides in and 45 minutes in.
Yeah, I mean, I don't know, we spent a lot of time on the supremum stuff, and
Oh, yeah.
that's all right. Yeah, I think we'll finish in 2 hours probably, maybe a little more. Okay, so I just want to make a comment, which is more of a preview if you go on to study the calculus of complex numbers eventually, but when I said that gamma is analytic, what I really mean is that gamma can be extended to an analytic function that takes complex numbers as arguments. Right, so we wrote down this integral that works for any real value of the z that we put in, or I keep writing x for some reason. So you put in, this is like a machine where you just feed in some value of z that goes in this exponent, and then this integral gives you some number just by finding the area under the curve. But when you study the calculus of complex numbers, you'll see a way of plugging in a complex number z, and then getting some complex number out of this integral by finding some sort of generalized area. And this allows you to plot the gamma function on the complex plane. So here's the imaginary part. This got cut off, but there's a real part of z at the bottom. So this is a real part of z. So you should really think of this as being like, here's kind of, x plus iy. So iy. And you can plug in points like, here's the value of, 2 plus 2i. So you feed in that complex number to gamma, and it spits out some complex number. It's very hard to graph complex numbers in a screen or in a two-dimensional plane, so people usually use colors. So what the colors here represent are the angle, if you write the complex number in polar coordinates, r e to the I theta. So the color here is the angle theta, and then these contour lines, which you'll study next week in 1802 already, these contour lines are telling you how the size of r changes as you move. So as you can kind of tell, the contour lines get closer together as x gets larger on the real axis, which is just the statement that factorial grows faster and faster as you increase the input. Okay, so this I think is something very interesting. And as we saw, gamma blows up at all of the negative integers, so that's where these really tightly clustered contour lines are doing. Okay, good. So we're already on to Act 2. So now these acts are going to be kind of short, just kind of showing you a cool thing that uses the gamma function in an interesting way. But before that, any questions on the historical stuff or the factorial or that colorful plot, the gay plot?
Nope. I do not have any questions.
Okay. All right. I think this is a very interesting topic. I first learned about this in a Splash class. It's actually taught by a chemistry major. I don't know why he was interested in this, but...
because he could be.
Yes, exactly. That's the MIT ethos, I guess. But okay, so in this section, let's just think about monomials. So let f of x be x raised to the power k, just a monomial function. So we know the power rule to take the first derivative of this function. It's very simple. You take d dx of x to the k, it pulls down a k, and this is kx to the k minus 1. Now you can take a second derivative, so this pulls down this extra factor of k minus 1, and I already have a typo, it should be k minus 2 up here. So pulls down a k minus 1, and we're left with x to the power k minus 2 upstairs. And we've known since chapter 3 for months now that you can do this over and over and take a third derivative, a fourth derivative, or any higher integer power you want. But now you might say, okay, what about non-integer powers? Can I define a fractional derivative or a continuous derivative, d alpha by dx alpha of x to the k, for any real number alpha? Let's start with positive, or let's start with the easiest possible case. What about a half derivative? Can we take the 1/2 derivative of x to the k, where by 1/2 derivative I mean that this thing should have the property that if we take the 1/2 derivative twice, so if we apply this operator twice onto x to the k, we want it to be the first derivative, kx to the k minus 1. So that's the question we'll try to answer. Can we find such a procedure that takes a 1/2 derivative?
So there's like no intuition for this.
Yeah, yeah. This is very abstract, right? I mean, it's not clear what this should mean yet. But
Yet.
well,
Oh boy.
let's just follow our noses. I mean, this is a very general pattern in math. When you want to ask some question that sounds not to make sense, like what would a non-integer dimension be, right? We were talking about Hausdorff dimension before. Like, what does it mean to be half-dimensional? The question seems not to make sense, but it's because you're thinking about the word in a restrictive way. We're thinking of dimension as how many coordinates do you need for the space, right? A line has one coordinate, the plane has two coordinates, space has three coordinates. Whenever that happens in math, that you're trying to ask a question that seems not sensible, it really means you just need to think of a different definition of the word in question, such that that new definition does not obviously give nonsense when you ask the question you're interested in, and then try to answer it. So if we try to ask this question about d alpha in terms of the existing definition of a limit as epsilon goes to 0, then this thing gives us nonsense. So first we'll try to look for a pattern that does not rely on that limit definition, which will render the question sensible, which I'll show you on the next slide. But I cut you off.
Does not make. I think that how I was going to word it. It's not nonsense, but it doesn't make a lot of sense.
Yeah, well, right now it's nonsense. I mean, this question is formally nonsense. So we have to rephrase the question to make it make sense. Okay. Well, let's first write down the pattern for all of the integers. So I already gave you the first couple. The first derivative of x to the k is kx to the k minus 1. The second is k times k minus 1 times x to the k minus 2. And you probably see the pattern now. Each time you take a derivative, you're going to pull down another guy, and then you're going to have some reduced factor upstairs. So can you guess the pattern and write down a formula for taking n derivatives of x to the k? So just give me some, well, first give me just a formula however you want to describe it, and then we'll rewrite it with factorials. But anyway, what should this look like?
So, I guess, let's see. This is going to equal to x to the k minus n.
Good. Times what?
Times the sum, pardon me, the product from, let me think. I guess 1 to n of k minus n.
K minus n. So let's just think about those bounds a little bit. So if n is 2, your product would give me k minus 1 and k minus 2. But we don't want k minus 1 and k minus 2. We want k and k minus 1. So I think we should just change the bounds so it runs from
negative 1.
Yeah, 0.
Yeah.
Good. And I should put n, I should put either. Good. But now I agree.
Yes.
Okay. Okay, so let me just write that out a little more explicitly to remind us of what that means. So that means times k minus 1, dot, 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 and then there's a k minus n, right? Okay, now the million-dollar question. Do you see how to rewrite this product as a factorial? Because factorial isn't quite what we want, because k factorial would be k minus 1 all the way down to 1. But we don't want to go all the way down to 1. We only want to go down to k minus n. So do you see a way to write a quotient of factorials, a different, some ratio of
That's what I was going to say.
Good. What is it?
I don't know what it is right off the top of my head, but I know that it can be done with quotients.
Well, let's figure out what it has to be. So,
is it k factorial divided by n factorial?
Well, let's see. So k factorial would give us k all the way down to 1. And we want to just delete all of the ones from k minus n minus 1, right, times dot, 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 down to 1. So you see what I mean? This goes all the way down to 1. We want to stop at k minus n. So how do you divide out all of the factors from k minus n minus 1 down to 1?
You let the bottom be equal to k minus n minus 1 factorial.
I think that's right, yeah. Because then upstairs we'll have from k down to 1. Downstairs we'll have k minus n minus 1 down to 1. So we're left with k down to k minus n. Good. I think that's right. Let's see the next slide if that's actually correct. I think I have the wrong answer here. Is that right? Because k, yeah, this is not right.
Check it.
Yeah, let's try k equals 3 and see if this is right. So this would be 3 times 2 times 1 over, or sorry, let's try k equals 3, n equals 2, for instance. Okay, so this would be over 3 minus 2 factorial x to the 3 minus 2, which is 6x. Now, is this equal to the second derivative of x cubed? Yeah, I guess it is, because you'd pull down a 3 and a 2, 6x. So,
Whoa!
okay, so this formula is right. Why is it k minus n and not k minus n minus 1?
Did you want to also divide out k minus n?
Did I want? I don't think. K minus n. I don't think we do, because we want that to be in the top. So now I'm confused, because this is supposed to be. Oh. Yeah, sorry, I'm being silly here. This is k to k minus 1. So there should be. How many factors should there be? Wait, I totally just confused myself. So wait, is this right, or is the thing that we said before right? Now I'm confused.
If k equals 3.
Yeah. Let's do bigger numbers, because I'm probably screwing this up because I have small numbers. So why don't we do k equals 4, n equals 2. So this is supposed to be a formula for the second derivative of x to the 4th, right? So d squared dx squared x to the 4th, which is supposed to be 4 times 3 times x squared. So which one is it? Is it k factorial over k minus n factorial? That one would be 4 times 3 times 2 over 2 times 1, which is 4 times 3. Or, yeah, it should be this one, I think. K factorial over k minus n factorial. So, k minus. Why am I confusing myself here?
You should have 12 times x to the second. Let's compare that to doing it ourselves.
Yeah, so we do have 12x to the second here, because this ratio is 4 times 3 times 2. Oh, wait a second. What am I doing? This is... Yeah, no, this is right, because the 2's cancel. So this is 4 times 3. So this formula is apparently correct. So why is that correct? K factorial over k minus n factorial is k times k minus 1 times dot 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 times k minus n, and then those all get canceled, right? So k minus n. So this thing doesn't have the k minus n factor left in it. I must be making some very silly mistake, because this argument just makes it seem like this answer is wrong, but we just checked that this gave the right answer, right? K minus n. You see the mistake I'm making?
I have no idea what mistake you're making. I can only keep playing in my head the SpongeBob you what.
Okay, well, apparently this is right though. So how many... let me do one more and then I'm going to stop confusing myself. So what if we had k equals 5, n equals 3? Maybe I need to go in higher. Well, let's go a little higher. So k equals 6, n equals...
I will say that for the x to the 4th case, I'm pretty sure that that would be equal to 24x to the second. Wait, no, sorry.
This should be...
Yeah, yeah, you were right with the previous one. Never mind.
Yeah, so this will be, I take one derivative, 6 times 5 times 4 times 3, and then what I'm left with should be x squared, right? And then this
Sounds
thing,
right.
is 6 factorial, is this question mark, 6 factorial over 6 minus 4 factorial. Yeah, this is right. Okay, good. The formula I've written here, now, okay, I'm an idiot. This is right, and something I said before was wrong. Yeah, because we don't want to go all the way down. Yeah, the formula I wrote on the previous slide was that we wanted to have factors all the way down to k minus n in front of this guy. But clearly we don't. We don't want the factors down to k minus n in front of this guy. We want all but the last one, right? Because you don't have a k minus 2 in front of this guy if you take two derivatives. The power that's left is always one less than the last factor in front of it, right? Because you pull down and then subtract one. That's where I was confusing myself. So what I said before was wrong. It shouldn't be k minus n minus 1. It should be k minus n, like this. This is right.
Okay. The idea is clear.
Good. Okay, but now you see the pattern. That was that took me longer than expected, but okay, so is it clear that this formula now works for any integer n?
Wait, was there a question?
Yeah, I was asking, is it clear that this pattern and this formula should work for any integer power n?
Yeah.
Okay. All right, now I'll ask you, how do we invent a formula for non-integer powers? So I'm just going to copy the formula from the previous slide. So naively, what we would want to do is say, all right, this should be the power of x, which is k factorial over k minus the number of derivatives we're taking, which is now alpha, apparently. So this is supposed to be, we think, k factorial over k minus alpha factorial, x to the power k minus alpha. So if we want to make this formula work, we wrote down this formula for only integers, and now we would like to change the right-hand side in some way so that it's true not just for integers, but for any real numbers. So what should I write to make that work and agree with the previous formula, the factorials, on the integers?
Equals gamma of k plus 1 over gamma of k minus a plus 1.
Good.
Times k minus a.
Alpha.
Times x to the power of k minus a.
Alpha. Yeah.
Alpha.
Good. Okay. Yes, perfect. So modulo my small confusion about what the denominator should be in that formula, now we see why gamma is useful. Because gamma gives you an automatic way to take any formula which works for integers because it involves factorials, and you simply replace all of the factorials with appropriate gammas shifted by ones, and now for free you get a formula which works for real numbers, continuous, not just integers. So indeed, as you say, if you just take those k factorial and k minus n factorial and replace them by gamma of k plus 1 and gamma of k minus n plus 1, you get this definition. We don't know if it makes sense yet, but this is one sensible way of defining the non-integer derivative of any monomial x to the power k. You just take this ratio of gammas and take x to the power k minus alpha. Okay, so
But does this have the derivative of half property you described earlier?
yes, it actually does.
Half derivative.
We haven't proven it, but surprisingly it does. Let's look at what this looks like, actually. So we need to know what some properties of the gamma function are. We haven't proven these, but, well, we proved in this one. So gamma of 2 we know is 1, just because of that factorial property before. What is gamma, if we want to take the 1/2 derivative? So if we want to let, for instance, alpha be a half and k equal 1, then we need, the bottom will be gamma of 1 minus a half plus 1, which is 3/2. So we have to know what is the gamma function at 3/2 if we're going to compute that. And as it turns out, you can just do the integral or whatever. Gamma at 3/2 is root pi over 2. So here's our first fractional calculus result. The 1/2 derivative of x is 2 over root pi, x raised to the power 1/2. What does that look like? So if we look at a graph, here is f of x equals x. We know the first derivative of that guy is, well, I'll write it with ddx to make it clear. So ddx of f is 1. And then the half derivative seems to interpolate somehow between them. So d1/2 by dx 1/2 of f is 2 over root pi times the square root of x.
So why does pi show up in literally everything?
Yeah, it's very mysterious, right? It's related to this mysterious connection between sphere volumes, which have to do with pi, and factorials, which I'll say a little bit more about later. But
Oh boy, that thing.
yeah, so this is mysterious. I haven't shown it, but it is true that this guy has sort of this composition property. If you do two of these fractional derivatives in a row, it's the same as doing one derivative with the sum of their powers. If you do d half twice, you get a derivative. And you can actually use this to get a smooth interpolation. So let me show you that picture next. So yeah, so this is on nice Wikipedia, so we can see this nice animation. So this, the green curve, as we're seeing this moving, fucker. Where did that go?
I believe in you.
I can do this. Good. Yeah, so as we see the green curve move, now we're taking the derivative of a half x squared and changing the order of derivative that we're taking. So as this green curve goes down, it's taking now the first derivative when it hits the blue line, the second derivative when it hits the red line, and we get a continuous smooth interpolation taking fractional powers of derivatives between each of these. So this is kind of a nice but mysterious, hard to interpret sort of operation, this fractional derivative. Again, I'm not
Wait, what point was it moving around?
What point was it moving around? What do you mean?
Is there any importance to where it intersects the y equals x?
Where it intersects. I don't know if that's super important, right? Because as the green thing is moving, we're just getting different functions. So it's just, I mean, the intersection y equals x, you mean when they align, when the green curve aligns with the blue curve?
I mean, I'm just thinking about following the point where the green overlaps with blue.
Okay, yeah, I mean,
I don't know. It's just a random.
yeah, that would just give you some transcendental equation. It would be x raised to some power equals, you know, a constant times x, which you could solve. Yeah, we could write down the answer for that, but I'm not sure it's super interesting.
Don't know.
Okay. Anyway, so this is actually all I'm going to say about this. I included this section to show you an example of how the gamma function is nice for generalizing some equation that appears to only work for integers. So
Does this imply the existence of half integrals?
yes, indeed, yeah. So there's actually a Riemann-Liouville differ integral. It's written J alpha. So J alpha of f is some operator acting on f where now alpha can be any positive or negative number. So if it's a positive number, J1 of f is the derivative, right? So df, maybe J3 halves of f is, you know, d3 halves, dx to the 3 halves of f, and then negative values, if you take a negative number of derivatives, then this thing is going to be basically an antiderivative. So this is an antiderivative of f with respect to x. So you can actually define an operator that smoothly goes between derivatives and higher derivatives. J0 is just going to spit back the function itself, and then negative j's give you integrals. So they're smoothly connected by this differ integral, as it's called, which I think is even written down on this page. Yeah, here it is. This, here we go. They write it as j, but it's, yeah, where's the name of it? Should be defined. Well, they talk about Laplace. Here we go. The Riemann-Liouville differ integral. Yeah. So you can do that. It's a totally well-defined object. You almost never study it in high school or even really in undergraduate courses because this is it's something.
Would you even study it as a grad?
Not really. No, you would only study this if it comes up in your research because it's actually something that it's a theory that hasn't been super well developed. It's actually a very niche area of mathematics, but I included it as an example of how gamma is nice for generalizing integer things to non-integer things.
Whoa.
Good. Questions on fractional calculus?
Nope, but before we go to the next act, I be using the restroom.
Okay, I will be here.
Yes.
Shit posting. I hit the shark, and then I realized I should have said that menopause is actually the end of Shark Week, so Shark Rip is more appropriate. Good. Okay. Okay. So another example. Yeah, as I said, today is really just a bunch of seemingly, well, actually unrelated places where the gamma function appears. So I will impose my bias upon you and talk briefly about where this appeared in string theory. But first, we need to discuss what the beta function is. And that will come about most naturally in talking about a sort of recurrence. Okay, so let's discuss what I mean by this recurrence formula for n balls. You already proved one of them, so if you remember this DC 21.3, I asked you to find the volume of a 4-ball, and there was a very natural way to do it, which is to slice the 4-ball into 3 balls. So in that case, you had the radius r equals 1, but here I'm just writing it for any radius. What you did is basically slice the 4-ball into 3-dimensional balls, which have volume 4/3 pi r cubed. And then what you could do is pull out the 4/3 pi r cubed, if you like, and then this thing basically just comes from, the higher dimensional generalization of Pythagoras to find out for each of those guys what volume do you need to integrate from minus r to r to get the total volume, right? So this is how you got, pi squared over 2 or whatever it was for the 4-ball volume, right? This slicing. But as you probably realized, there's nothing special about going from 3 to 4 in that setup. You could do this for any number of dimensions. So if you happen to know what the n ball volumes are, or say the n minus 1 ball volumes, you can get basically, you can get the n ball volume by going from minus r to r of the n minus 1 ball volume, say of radius r. Well, I guess this should really be x because we're still integrating over x. Dx, and then by symmetry I'm just going to say, okay, well, we know that this will only involve squares, and squares are even functions, so by symmetry, instead of going from minus r to r, I can just say this is twice the integral from 0 to r of the n minus 1 of x dx, and then I've just written that here. So I've pulled out the 2, done the symmetry to kill the bounds of integration that are negative, and then written this formula here, which the only thing that changed is that these powers now depend on arbitrary n's. Okay, so is the idea of that slicing to get that formula Gucci for you?
The idea is clear.
Good. Okay, now we're going to use it. So a challenge for you. Here's the slicing formula. We're going to get a recurrence, so a relationship that gives the volume of an n ball in terms of an n minus 1 ball. And the trick is to use the following change of variables. So you let u be x over r quantity squared, because that's the guy that appears inside here. And then you do this u sub and get some nice result. So, so I'll ask you what happens when I make that u sub and what pops out.
All right. We let u equal x divided by r quantity squared, and thus du equals 1 over r squared times x. Yeah, 1 over r squared times x squared. I don't know why I felt the need to break that into... Wait, no. Times 2x.
2x dx. Good. Okay. Or in other words, we can solve that and get dx is what? R squared du over 2x, I think? Is that right?
Yeah.
Okay. So then what does the integral turn into after making that tasty sub?
That becomes the jazz in front, and then... Ah, yeah, I was about to say, why is there an equal sign there?
That's no good.
That's no good. So, I guess start with bounds of integration.
Yeah.
So, 0 becomes, let's see, we are substituting in, it is simply going to still be 0. And r is going to become 1.
Good. And the integrand?
Let's see. Integrand. 1 minus, well, begin parentheses, 1 minus u squared, end parentheses.
Not squared, right? Because u is the thing squared, right?
Yeah.
Right.
Yep.
Good.
That is clear now.
And then this all
To the power of n minus 1 divided by 2.
Good. What about the dx?
And the dx is going to become r squared du all over 2x.
Okay. But we've done something illegal because we've done our u sub, but only gone part way because we've left one appearance of u and one appearance of the old variable x. So we have to get rid of x and substitute in its expression in terms of u, but that's easy to do. What happens if you solve this equation up here for x?
So x is equal to the square root of u times r.
Good. Okay, so I'm going to take that and...
That's yeah, I see root u times r and I think root pi times r, and I've been scarred.
Yeah. Scarred from painful algebra, I guess. So, okay, good. 2 root u times r. Okay. And then, thankfully, this 2 kills the overall 2 outside, and I'm going to pull that r squared out. So I guess we've got an r squared v n minus 1 of r integral 0 to 1. If I'm doing my algebra correctly, this is this thing, and then, oh wait, sorry, this shouldn't be r squared because there's an r downstairs, right? This r downstairs kills 1 r upstairs. So it looks like that. And then u to the power minus a half, I think, if we can write that as. Okay, is this right?
I think that's actually u to the power of 1/2. Wait, no, never mind, sorry. Yep, it is u to the negative 1/2.
Okay, good. Yeah, units are right, because an n-dimensional volume has units meters to the n, r has meters, this is meters to the n minus 1, so it all looks good. This is dimensionless, no units. Okay, so I think this is right, and indeed it looks like that's the right thing, so I can erase now because this is all actually correct. Indeed, with that u substitution, you get this nice recurrence relation. So the n ball volume is r times the n minus 1 ball volume times this new interesting integral that we have not met before and we cannot evaluate in terms of elementary functions. So when you see a new integral that you cannot evaluate, you define a new function whose name is whatever thing appears inside that integral and see if you can do anything interesting with it. So we'll define a new function called the beta function. So the beta function takes in 2 arguments, so it depends on x and y, and it's just the integral from 0 to 1 of u to the power x minus 1 times 1 minus u to the power y minus 1. So a couple things to note. One thing is that if we just match up these powers here, the value of x that we need to get, let's see, I think I have these wrong here. Yeah, sorry, these are backwards. Yeah, the power of x that we need for these guys to match is 1/2, because down here, 1/2 minus 1 gives us the minus a half. The power of y that we need here, I think, matching these guys, is n plus 1 over 2, because n plus 1 over 2 minus 1, well, 1 is 2 over 2, that's n minus 1 over 2. So then those two match. So that means that we can write the result that we just got by saying that the n ball volume is related to the n minus 1 ball volume times a beta function. Beta is just this integral with some values. Okay, is that, I mean, maybe the motivation for introducing this is not clear, but is the manipulation that we did at least clear?
Yes, everything is clear.
Okay, good. Let's, okay, so here we go.
More challenges!
Yes. Okay, so here's the formula that we just wrote again in terms of a beta function now. But we also already have a formula for any volume of any n ball, for any n. So what we can do is we can take this formula, plug it in the left side for Vn, then we can take this formula and replace n by n minus 1, which gives us the n minus 1 ball volume, and plug that in here, and replace both of those, and then solve for the beta function. And that'll give us an equation relating beta and gamma after some algebra. So I'll just ask you, if we do that, what should I write down and what is the algebra?
All right.
It's a very resigned all right.
So we're going to have left side pi to the power of n divided by 2 over gamma n divided by 2 plus 1
Good.
Times Rn equals cough cough pi to the power of n minus 1 divided by 2, well, all divided by 2,
Good.
divided by gamma of n minus 1 divided by 2 plus 1.
So 1 over 2 plus 1. Good. Then what else?
Times r to the n minus 1. and then times r to bring that,
Right? Oh, right, the r. Sorry.
well,
Good.
to bring
Yeah.
times r, which brings that to r to the n.
Good.
So we can simply erase.
And then the beta, right?
Times beta of jazz, n plus 1 over 2, comma 1, 2. Well, 1 over 2.
1, 2.
1, 2, 3, 4.
Good. Okay, so the nice thing about this is a couple things happen. The r to the power n on both sides cancels, so I'll erase that. So what happens with the pi's? What factor of pi am I left with?
It looks like...
Maybe it's easier if I write that.
Okay, yeah. We can rewrite it as n over 2 times pi of 1 over 2.
It was a minus, but yeah. Good.
Oh.
Good. So then what happens?
So we are going to have a pi to the power of 1 over 2 left over.
On the left, yeah.
Yes.
Because you multiply. Good. Okay. So that's also known as root pi. Okay, so we're almost done. Then what happens when you solve for beta of n plus 1 over 2? So just move everything to the other side and tell me what we get.
So, let's see. That is equal to gamma, well, let's see. Well, it's equal to root pi times gamma of n minus 1 over 2 plus 1 all over gamma of n over 2 plus 1.
Good. Gamma of n over 2 plus 1. And I'll simplify that a little bit. So as it turns out, square root of pi is gamma of a half. So I'll use that to substitute in the top. So that's gamma of a half. I'll just get a common denominator here. 1 is 2 over 2, and n minus 1 plus 2 is n plus 1. So this is gamma of n plus 1 all over 2 divided by gamma of n over 2 plus 1. So this is beta. So this is interesting. Beta takes in two numbers, and it looks like beta is a ratio of gamma functions that are some combination of those numbers, right? This is like gamma of the second argument times gamma of the first argument times something which looks like gamma of the sum, maybe, of those arguments. Yeah, because if you add these two, the two halves give you a 1, and you're left with an n over 2. So this n-ball recurrence thing is telling us that the relationship between an n-ball volume and an n minus 1 ball volume has some connection to the factorial. So I'm not saying this very precisely, but this is one way of understanding why factorials are related to n-ball volumes, because a factorial has a recurrence relationship in the sense that n factorial is related to n minus 1 factorial by some certain functional relationship, because the factorial is kind of recursive. The volumes of n-balls are also recursive in the sense that Vn, the n-ball volume, is roughly, integrating slices of Vn minus 1. So there is a relationship that gives you the n-ball volume in terms of the n minus 1 ball volume. It's just that that relationship is a little more complicated than just multiplying as it was in the factorial. It involves an integral. So that complication is why these equations look like a mess, but really at the heart of it, this is telling us why gamma, which is really related to factorials, also appears in n-ball volumes, because n-ball volumes are recursive like factorials are recursive. Okay, good. Let me write that more cleanly on the next slide. So this is just everything that we did a moment ago, just plugging in, as you said, canceling the factors of pi as appropriate, plugging in root pi as gamma of a half, and then this is the result that we found. So this is a specific case of a more general equation. So it's generally true that the beta function on any x and y, as I've written there, is gamma of the x, the first guy, gamma of the y, over gamma of x plus y. Now this might remind you, except for some signs, this might remind you of something you've seen before. Do you remember when you were proving the power rule and you had this formula a plus b raised to the power n? It was like a to the n plus, there was a bunch of terms that looked like n choose k. times, a to some power minus k, b to the k. Do you remember these symbols?
I recognize them, but could not define them.
Okay. They had a similar definition, n choose k. When you used those before, the definition was n choose k is n factorial over k factorial times n minus k factorial. And these were called binomial.
I remember.
You remember this?
I remember this.
Yeah,
I cannot remember how we applied it.
You were using it when you proved the power rule, because you wanted to know what, a plus x to the n was. And you wanted to know for all of the terms. And they're written in terms of binomial coefficients.
Okay.
So here's another example of a formula which worked for integers, right? We had something which involves a binomial coefficient is a ratio of factorials of integers. And now beta, this is why we use the letter b, it's beta for binomial. Beta is like a continuous version of the binomial coefficient, except for two changes. One, some of the signs are flipped and the product of the two things is upstairs rather than downstairs, which I'll explain in a minute. So this looks a little different from this guy, but they still involve a ratio of 3 different factorials, except now we're using the continuous version of factorial. So instead of the factorial for the binomial coefficients, for beta, you use the gamma function. So it's gamma of these 3 guys. So anyway, you should think of beta as being related to a continuous version of the binomial coefficients you used for the power rule.
Random side note.
Good.
I mentioned to Shu today that I was working with Lansgrom, and he was like overjoyed.
What did he say about this exactly?
He said that I think he more or less said that he was proud of me for going out of my way to take on multiple research projects and stuff.
Okay, good. I'm glad he said that. It could have gone the other way. It could have been like, oh, well, you're using someone else's resources, so you can't work with me now or something. So I'm glad he responded positively. All right, that's very good to hear. Cool. Okay, so let me explain that side comment. So as we said, from the proof of the power rule that you did before, we had these binomial coefficients, which tell you the way of basically choosing k objects from a collection of n objects where they're indistinguishable or something. So as I was just trying to explain, the beta function is a continuous version of the binomial coefficient except with some rearranging. So I'll show you the rearranging now. This is the equation that we showed a moment ago by using the sphere slicing argument. And if you just do a little bit of algebra to rearrange these, you take this continuous version of if you take the discrete version up here of the binomial coefficients and replace all of the gammas with, the factorials with gammas. So I'm just trying to go from the discrete version to the continuous version down here. So I'm replacing n factorial by gamma of x plus 1 and so forth. And if you do that and then just plug in for each of these gammas their expressions in terms of the betas, you get something which looks like this. So the continuous version of a binomial coefficient is almost related to beta, except for historical reasons, it has this one extra factor and the beta appears downstairs. So it's kind of flipped. But that's not super important. The punchline, the point of this whole story is that beta is a continuous version up to some subtleties, like this flipping here, up to some small issues. Beta is a continuous version of the binomial coefficients, and for this reason beta is going to appear in a key way when we do probability. So there'll be beta distributions that are related to flipping a coin that may or may not be fair, and choosing among different trials, a number of successes, which will all be related to beta, very importantly. But I'm just introducing it now in the context of spheres. So anyway, good. This is our second new friend that we've met. So we've met some nice special functions. We met gamma, now we met beta. We've met some other functions before. We met cosh and sinh in the past. You've met the Lambert W function, which was the inverse of xe to the x. So one thing I'm trying to do with this calc group is to expose you to a lot of interesting special functions. So here are some of the ones we've had so far, and we're going to do more. But okay, thoughts on this before the last act, I believe.
Well, I had a thought and I forgot it.
That's why you're supposed to interrupt me. As soon as you have a thought, shout it out. You can't remember what it is?
I think it was related to the factorials, and I just had it again, and then it slipped away.
About the continuous version of the factorials or the binomial coefficients?
I hope I remember it.
Lost forever. A log thought sent to the void. Okay, well, I hope if you remember, shout it out. Without, don't wait this time. But okay, yeah. One more comment, two more comments on this, and then the last thing. So, surprisingly, string theory didn't really start as a theory of strings. So this Veneziano guy, whose name, this equation bears, he was trying to understand the physics of the strong nuclear force way back in '68. And in doing that, he considered a certain scattering experiment, which today we would describe as follows. If you have like some beam of strings, so you have some incoming beam of strings that you fire to the right, so a bunch of open strings, so strings like this, and then you have another beam of strings coming from the right side, so strings like this, and then these beams of strings kind of meet at some impact point, so a string coming from the left hits a string coming to the right, and there's some collision, and then they're going to scatter off, so one of the strings maybe goes this way, and another of the strings maybe goes some other direction, so they come in and scatter off or something. You could ask the question, if I do this with a lot of strings, so they're going to be flying off in all different angles and things like that, and I try to measure how many of them go at each angle, say theta, as a function of, say, the energy of the beams that I'm shooting these guys in. It's a classic question you ask in quantum field theory. Is what is the number of strings you get at each angle? And the answer to that question, you write it like this.
I'm going to ask a question before we go any further.
Good. What's the question?
I still have no idea what strings are supposed to be.
Yeah.
Are they... Is it like a subset of the already subatomic particles?
Yeah, they're not made out of anything. Strings are supposed to be the fundamental objects, right? So they're not made of anything. They're just the string theory strings like have no rest mass. They're just made of pure energy, whatever that means. So they have no substructure. The string theory strings can vibrate in such a way that make them look like the fundamental particles, like protons, electrons, positrons, whatever. Yeah, so the string theory strings are just the fundamental objects. Like they're the smallest. They're the end of the tower of questions. What is that made of, right? Like you ask what people are made of. They're made of cells. Cells are made out of molecules. Molecules are made of atoms. Atoms are made out of electrons and protons. Protons are made out of quarks. Quarks are made out of strings. And that's where it stops, right?
But what? They must be made out of something.
Well, I don't see any argument for why it must be.
Well, it can just be disturbances in a field, I think is how some other people described it.
Yeah, well, that's kind of a different answer. I mean, if you don't have string theory, you could say that electrons and positrons are disturbances in quantum fields, and that's what you do when you study quantum field theory, and that gives you a perfectly reasonable answer. You can say that those are fundamental and there are no strings beneath them, and you can calculate, and you can do very well with that. But if you want to understand, okay,
Do very well, you say.
Yeah, do very well in the sense that like you will.
Can you do it perfect?
You can do it you can do it and get answers that agree to the 8th decimal place with what people get at CERN, which is as far as you can measure it. So it is the most successful scientific theory man has ever written down. You write down quantum field theory, it gives you extraordinarily precise predictions. It says, go build a particle accelerator, you will get these numbers. And then people build the particle accelerator, they measure those numbers, and to as close as they could possibly get with the accuracy of their detector, it matches those numbers. So it's the exactly correct answer. You don't need string theory to get better predictions. The predictions are already exactly correct, just with quantum field theory.
So you just want to go one step further.
Yeah, I mean, I just want a conceptual understanding for why those quantum fields behave the way that they do.
Okay.
Good question, though, or good comment. Other thoughts?
Nope. I don't expect you to know everything.
Wait, what is that supposed to mean? Did I not answer the question well enough?
No, I was thinking about asking how something can have mass, but that's the question.
No, that's easily
What
answered.
is mass?
The question of mass is generated differently for different subatomic particles, right? So for WZ bosons, for example, mass is generated by the Higgs mechanism, which is well understood and gives you very precise predictions about W's and Z's that you can test. For other particles, the mass comes from their rest mass of the field. For particles that are associated with gauge symmetries like U1 and the photon, it's massless. I mean, this isn't some deep philosophical question like where does mass come from? Like, no, we have the answer. I mean, we understand mass generation. Yeah, I mean, I think I'm more than capable of answering those questions at least. Good. Other questions?
Now, no calc slides.
Okay. Good. Okay, so, well, the point I was making is that if you ask that question about scattering strings, if you scatter strings in two beams and then do some measurements about how many strings in those beams scatter off at various angles.
Wait, what says that they even interact?
Oh, yeah, they could not interact. In the theory that we've written down for open strings. So, I mean, this is the answer given a certain description of how open strings behave. Right? If they didn't interact, then of course they would just pass through each other, and the answer would be you get 0 strings for all angles except plus or minus, or 0 and 180 degrees. Right? That's one possible answer.
Okay.
But with
so there's the assumption that they do.
Yeah, well, it's not. I mean, you can prove they have to behave in a certain way just by very general principles. But yeah, so
Okay.
Knowing how they interact. So if you know what the string Lagrangian is, so this is under like the the Nambu-Goto action, which describes the string under this assumption about the way the string should behave, you could ask how many of them are you going to get at each of those angles, right? And you get an answer which is written in terms of an amplitude. That's roughly something you would use to get the numbers at each angle. So you say, okay, I don't see any angles in here. Well, okay, so the angles are kind of hidden in these k's. So this is if you have some guy coming in at k1 and k2, and the output guys going at k3 and k4. These guys are vectors that carry some information about the angles, so these k's are secretly hiding some angular dependence and some energy dependence. So what you should think of this equation as is the right side takes as input the momentum, some vectors that describe how these strings are supposed to be scattering, and then the output, the left side, after evaluating the gamma function, gives you some number. How many strings will scatter with those momenta that you fed into the right side? Good. So this is a famous, the first equation of string theory. You can use this to describe hadron resonances at CERN, but it's really started the field. And the reason I'm bringing it up now is you probably see just by looking at the equation we wrote previously, this beta is a ratio of gamma functions with some x, y, and z. As it turns out, the first equation of string theory is exactly a beta function. So this is exactly a ratio of gamma functions. Gamma of x, gamma of y over gamma of x plus y, where you can kind of see the thing in the denominator is x plus y, because here's a -1 adds to a -2, and so on. So the punchline is that this crowning, first achievement that started the field of string theory is the beta function. Beta function for some particular choice of arguments. Good. Famous equation. And we'll have more to say about the beta function when we go on to probability. But for now, I'll just leave you with this nice picture. Here's what the beta function looks like. Remember, it takes in two arguments, x and y. So if you feed in an x and a y, you get some answer, which is a number, and the number is here shown with color as shading.
Familiar from end of December.
Familiar from end of December. Where did you see this in December?
Never mind.
Okay. Do I have 2 acts left, or is this the last one? No, this is the last act. Okay, good. Good, last act and about 20 minutes to go. Okay, so just to review, we've seen now a few places where the gamma function is useful. It appears in sphere volumes, it appears in a smooth version of the factorial. We saw that it shows up in the fractional derivative and in the beta function, which appeared in string theory. So now one more thing. When I said we were going to define a new function and there will be some special numbers associated with it, I want to tell you about the special number associated with gamma in the same way that pi is related to sines and cosines, or E is related to log, gamma, lowercase gamma, is related to capital gamma in a key way, which you've already met before, actually. But okay, so let's just do some more. Good. Here's how the relationship works. So again, the review, here's the gamma function, which came from sphere volumes or a continuous factorial. We met the beta function, which can be written either as this other integral involving, these t and 1 minus t's, or as a ratio of gamma functions. You might ask, what now about derivatives of the gamma function? Hopefully you've done calculus long enough that whenever you meet a new function, you naturally ask, okay, what are its derivatives and integrals? So we will ask about the derivative of the gamma function. And in fact, because the gamma function grows so quickly, it's like a factorial, it's easier to analyze not its derivative, which will get very large, but the derivative of its logarithm. So you may have remembered this trick we did way back in chapter 3. You take the logarithmic derivative of something. By logarithmic derivative, I mean just take d dx of log of the function you care about, and by the chain rule, that gives you a 1 over f times the derivative of the inside, or f prime over f. So we're going to take the logarithmic derivative of the gamma function. And that thing, for reasons which are unclear, I don't know why digamma was chosen, but whatever, that is called the digamma function. So digamma, written with the letter psi, is d dx of log gamma, or gamma prime over gamma. And you already used that in a daily challenge. But questions on digamma before moving on?
So how does this help us find the derivative of gamma?
Well, it's not helping us find it. We're defining it, right? I mean, we're not trying to compute its derivative. We're saying its derivative is some other function. Let's study the properties of that function.
Okay.
Okay, good. Well, okay, so here's a first property, a recursion relation. So we know that gamma satisfies this important relationship which acts like a factorial. So by taking derivatives of this thing and massaging it, we should get a similar recursion relation for digamma. So I'll ask you how to do it. If I take derivatives and then divide by appropriate things to turn these into digammas, what relationship do I get for the digamma function?
So the hint is telling us to differentiate?
Yeah.
Okay.
So if I take the derivative of both sides of this.
That's going to be... Let me think. Gamma prime z plus 1 equals z gamma prime z.
Product rule much?
Yes. Yeah, that's going to be z gamma prime z, z gamma prime z plus gamma z.
Okay. Gamma of z. Yeah. Okay. Okay, so we want to express this in terms of digamma. So digamma is gamma prime over gamma. So how can we divide this and get some expression in terms of digamma?
Let's divide each side by gamma of z plus 1.
Good, okay. Gamma of z plus 1. We'll have to do some massaging now, because on the right side, these things are not quite the ratio that we want, but we already have an equation telling us gamma of z plus 1 is something else, right? So on the left side, this is digamma.
Gamma of, that equals gamma of z plus 1, the right side. The right side's left term equals z, we see that z's are going to cancel 1, so we pull the 1 out, and we have a gamma of z.
Well, no, you'll have gamma prime over gamma, right?
Oh, yeah. Gamma prime over gamma.
There's a gamma prime here, and then you're going to put the downstairs will be z gamma of z, and the z's cancel, so you're left with gamma prime over gamma, right?
Yeah, which is equal to the...
which is digamma, right?
Digamma. Good. Yeah, that's the word I was looking for.
Good, okay. And what about this guy?
And that is going to be, if we pull out the 1 over z.
Yeah, 1 over z. perfect. So this is the recurrence relation for digamma. It looks a little weird, right? The gamma function recurrence was like a factorial. You add 1, it's like multiplying, so you're multiplying down. The digamma function tells you if you add 1 inside, that's like adding 1 over a number outside. So you can recurse this to find out what gamma looks like on the integers. Sorry, digamma looks like on the integers. And so let's actually do that. Repeating what you just said, take the derivative, use the product rule, divide by these things, put the z gamma of z's, cancel things, you get a 1 over z and a gamma prime over gamma, which is digamma. That gives the equation that you just told me. This thing down here in pink. And then now a second challenge. We want to talk about these harmonic numbers, because these will appear when we start iterating this digamma procedure. So the harmonic numbers ask you to add up all of the 1 over the integers up to this subscript n. Right, so let's just write some of them. So h1, well, there's only one guy in the sum, so h1 is 1 over 1, which is 1. h2, you add up all of the inverses, so 1 over 1 plus 1 over 2. This pattern's
equals 3 over 2, and so on.
Yeah, it's pretty obvious, so 1 over 1 plus 1 over 2 plus 1 over 3. I'm not going to simplify, but you get the point. Okay, so now I'll ask you, can we find a relationship, if you're allowed to assume we know what digamma is at 1, which is minus this thing, and then we know it satisfies this relationship where if you add 1 inside, that's kind of like adding a 1 over z outside. So I'll do the first one for you. Gamma of 2 using this formula when z equals 1 is apparently minus gamma plus 1 over 1. And then you can see this is going to continue. So what are the next few, and then what's the general pattern if we use this recurrence?
So gamma 3 equals negative digamma 3 equals negative lower gamma plus 1 over 1 plus 1 over 3?
So the recurrence tells you to have 1 over the old argument, right?
Oh, so z plus 1 equals... Okay, thus it is 2.
Yeah. Good. So that's minus gamma plus the harmonic number h sub 2, right?
Yes.
Okay. So what's the general pattern, if you can guess? What's digamma?
So digamma of n equals negative lower gamma plus hn?
Hn minus 1, I think, right?
Ah, yes.
Because for 3 it was 2. In general, it'll be hn minus 1. Yeah. It's always 1 fewer, because this guy, the 1 over z on the right, is 1 less than the guy inside on the left.
Yes, because of the presence of the 1 over 1.
Yeah. Okay, so what we've learned here is the derivative of the gamma function is somehow related to these harmonic numbers, the sums of the inverses of the integers. So up to this issue about the value at 1, which we haven't computed yet, digamma is related to the sum of the first n minus 1 inverse integers plus some constant. This gamma, this lowercase gamma guy. Okay, so this relationship is behind why digamma appears in a lot of number theory and probability and counting problems. So I'll list some of the places. Oh yeah, here's another place where it occurs. When people first learn about this constant, this lowercase gamma, this Euler-Mascheroni constant as it's called, which we've defined as negative digamma of 1. People usually first learn about this as a certain integral or a certain area. So here's the integral. If you take the integral of minus 1 over x plus 1 over the floor function of x, so this is just adding up in this picture, so the kind of brown area at the bottom, so this is the integral of positive 1 over
So I may as well interrupt.
Yeah.
That definition doesn't tell you a lot about what it means.
Yeah, absolutely. Yeah, this is not very intuitive. Sure. Good. So the lower integral is this integral of 1 over x, and this guy up here is this integral of 1 over the floor function of x, dx. So the difference between them is this blue area, and as this thing goes off to infinity, the sum of all of these increasingly smaller patches gives you this lowercase gamma, which is about 0.577.
Oh, that's familiar.
Yeah, indeed. So this is one way of defining it. As you say, it's not entirely clear why this definition would be useful. It appears more naturally if we define it as, the value of some function we care about, like digamma at a point. But this guy, this way of defining it, makes it clear why this thing should be related to these harmonic numbers. By harmonic, I mean 1 over integers, right? Because we just saw that digamma is related to a sum of these 1 over integers, and then here, this step function behavior at the integers gives us exactly that sort of harmonic number behavior. Okay, so here's one way of defining it. The derivative of digamma is another way of defining it. And I just want to flag some of the other places where this appears, because this lowercase gamma is quite special. As I've said before, it's basically the version of pi for trigonometry, but except for the gamma function, or the analog of e for logarithms in the gamma case. So this thing appeared in your daily challenge with the coupon collectors problem, right? With the the expected number of days, time t, you need to collect all of the coupons. Was supposed to go, the linear piece went like gamma times the number of coupons, plus there were some other junk corrections. So gamma could be defined as like the linear piece in the coupon collector problems.
Coupon.
Coupon or coupon, however you want to say it. But I'm now grading quantum field theory problem sets, and every fucking problem has gammas all over the place, because when you do regularization of Feynman diagrams to compute quantum field theory amplitudes, this lowercase gamma appears all over the place. And since this thing is related to these harmonic numbers, right, these sums from k equals 1 to n of 1 over k's, you might think that this lowercase gamma would appear in number theory, and it does. So this guy appears in bounds for prime gaps. So if you study the prime numbers, or if you study the number of divisors a number has as it gets large, or the Euler-Totient function, which are all important in number theory. Totient has to do with coprime integers. This lowercase gamma will appear there as well. So yeah, it appears there's a whole list, which I will conclude on, I guess, because that's the last slide. Yeah, there's this whole list of places. So here's the picture I stole, but here's lots of places where this constant shows up in Laplace, in the digamma, in the gamma function, in the totient, in the Feynman diagrams, as I said, in the coupon collector problem is down here. So it's an important number. It shows up surprisingly all over the place, but it's just somewhat less intuitive than some of the other famous numbers in math like pi and e that you can kind of just see quickly from a circle. But
would you say that shows up more or less often than e and pi?
Less than e and pi, but it's it's in the top 10 probably. It's after those guys. It's one of the runners up. Good. Okay. Fine.
I have things to do.
Yes, you have.